Okay, so welcome to lecture 2 of week 8, and we are in chapter 2, which is on sequences and their convergence. And so far we have seen what's the definition of convergence of a real sequence to a real number, called its limit. And we have also seen the theorem that monotone and bounded sequences are convergent, the theorem on the algebra of limits, and the sandwich theorem. So today the aim is to finish chapter 2, and there's one topic remaining, which is on subsequences and the Bolzano-Weierstrass theorem. So the Bolzano-Weierstrass theorem is an important result in analysis which says that every bounded sequence has a convergent subsequence. Now we know what's a bounded sequence and what's meant by the convergence of a sequence, but as yet we do not know this word, what's meant by a subsequence. So we'll begin our discussion today by explaining what's meant by a subsequence. So before we give the definition, well, a subsequence is roughly what the name indicates. It's a sequence. Sub indicates that if you have a sequence, then we are picking out some of the terms, but the only catch is that we should pick out terms in the same order. Okay, so we are not allowed to change the order. Okay, so here is the formal definition. So suppose that an is a sequence and you have a infinite list of strictly increasing natural numbers. So n1 is strictly less than n2, strictly less than n3, and so on. Then we use these as the indices and pick out the corresponding terms from the old sequence. So you get the new terms an1, an2, an3, and so on corresponding to these indices. Then this sequence ank, where k runs over n, is called a subsequence of an. Okay, so the terms of the subsequence are an1, an2, an3, and so on. Okay, corresponding to this list. But of course, there are many such infinite lists of strictly increasing natural numbers you can make. So any sequence has many subsequences. So in fact, any sequence is its own subsequence. Why? Because you can take as the list of these numbers simply as the natural numbers, and then this an1, an2, an3 are simply a1, a2, a3, and so on. So that's the old sequence itself. But for example, you could take this as the list of even numbers, yeah, and then you will just get the subsequence a2, a4, a6, and so on. If you take the odd numbers over here, then you get the new subsequence a1, a3, a5, a7, and so on. So any sequence has lots of subsequences. So let's see some concrete example. Suppose I look at this sequence whose nth term is given by 1 by n. So the terms of the sequence are 1, half, 1 by 3, and so on. Okay, so this is a sequence we have seen many times. Let's see some subsequences of this. So if I take as the list of indices as the even numbers, yeah, 2 is strictly less than 4, is strictly less than 6, and so on, and pick out the corresponding terms from over here, we get the subsequence 1 by 2k, where k is in n, right? So the subsequence has the first term half, second term 1 by 4, third term 1 by 6, and so on. If I take as my list of indices the perfect squares, right? So nk is k square. So these indices which we are taking are 1, 4, 9, 16, 25, and so on. And then the corresponding subsequence we get is 1, 1 by 4, 1 by 9, and so on. This sequence 1 by k square, where k belongs to n. If I take the powers of 2, the subsequence is formed by taking the second term, the fourth term, the 8th term, the 16th term, the 32nd term from this sequence, and so the subsequence is 1 by 2 to the power k, where k belongs to n, and the terms of this subsequence are 1 by 2, 1 by 4, 1 by 8, 1 by 16, and so on. As this list of indices, we could, for example, take the prime numbers, okay, arranged in increasing order. So 2 is less than 3, is less than 5, is less than 7, and so on. And nk is the kth prime in this list. Okay, since there are infinitely many primes, we know that this list is infinite. And then the subsequence I get is 1 by pk, where pk denotes the kth prime, and we get the subsequence 1 by 2, 1 by 3, 1 by 5 of this sequence. Let's look at this sequence whose terms are 1, half, and then I take the fourth term from here, and then the third term, 1 by 5, and the rest is the same. Now each of these terms does appear over here, but we have violated the order. We have taken the fourth term before the third term, and that's not allowed. You see, this list of indices has to be strictly increasing. So the terms in the subsequence should appear in the same order as in the original sequence, whereas here you are getting the fourth term before the third term, right? So this is not a subsequence of the sequence. Okay, so we now know what a subsequence is. One interesting question is whether whatever property the sequence has, whether that is inherited by the subsequence. And we will now prove the theorem that if you take any subsequence of a convergent sequence, then this subsequence is also convergent. So this property of convergence is inherited, and in fact the subsequence converges with the same limit. Now to prove this, we will need the following observation, and this observation is important to deal with proofs involving subsequences. So this observation is the following. Whenever you have an infinite list of strictly increasing natural numbers, okay, n1 strictly less than n2, strictly less than n3, and so on, then in fact you have that the kth term is always bigger than or equal to k. So the kth natural number in this list of strictly increasing natural numbers is always at least as big as k. Okay, so let's prove that, and we can prove this result by induction on k. So if k is equal to 1, then this inequality is saying that n1 is bigger than or equal to 1, and that's of course true because n1 is some natural number, so of course that's bigger than or equal to 1. And let's suppose that nk is bigger than or equal to k has been established for some k, and then we'll prove it for k plus 1. So the k plus first number in this list is of course strictly bigger than the kth number because we are assuming that this is a strictly increasing list. But by the induction hypothesis, nk is bigger than or equal to k. So what I've got is that this natural number is strictly bigger than k. But if it is strictly bigger than k, it is at least as big as the successor of k, right? So nk plus 1 is bigger than or equal to k plus 1. If nk plus 1 is strictly bigger than k, then nk plus 1 is bigger than or equal to k plus 1. Okay. So by induction, we have completed the induction step. And so by induction, this result is true for all k's. Okay, so whenever you have a strictly increasing list of natural numbers, then the kth number in that list is at least as big as k. Okay, so this is an important thing to remember because many times in proofs involving subsequences, you need this thing. So here is already an instance where we need this. Let's prove this theorem that any subsequence of a convergent sequence is itself convergent, and with what limit? Well, the same limit as the original sequence. Now, so what we are learning over here is that this property of convergence is inherited by subsequences, and as one of the homework problems you also have to look at other such properties. For example, if the original sequence is bounded, then in fact any subsequence is also bounded, and some other thing. So it's a true or false exercise, so you have to either prove the statement or give a counterexample. Anyway, so let's prove this theorem now, which I just mentioned, namely that any subsequence of a convergent sequence is itself convergent with the same limit as the original sequence. So suppose the original sequence is an, and suppose it is convergent with limit L. And suppose that a and k is a subsequence of an. And I want to show that this a and k is also convergent with the same limit L. Okay, so what do we have to show? We have to show that given any distance epsilon positive, there exists an index such that if I take the index little k beyond that index, I have that the distance of the kth term to the claimed limit, which is L, the same as the original sequence, is smaller than epsilon. Okay. Now we do know that the original sequence is convergent with limit L, and so for this positive epsilon there exists a index capital M such that for all little n beyond this index you have that the nth term's distance to L is smaller than epsilon. Now I'm going to take the same M as my milestone index over here. So I'm going to show that for every little k bigger than capital M, you have that the kth term of our subsequence, its distance to L is smaller than epsilon. So to do this, first of all, let's notice that for this capital M, you have n capital M is bigger than or equal to M by our observation over here, right? And so when the little k is bigger than capital M, we of course have that nk is bigger than nm because this was an increasing sequence, and moreover by our observation this is bigger than or equal to m. So this nk is an n of this type, it's bigger than capital M, and so this has to hold. So a nk distance to L is smaller than epsilon, and so we are done. So given any positive epsilon, I have managed to produce an index such that for all the little k's beyond this m, you have that the kth term of this sequence is its distance to L is smaller than epsilon. In other words, this sequence a and k indexed by k is convergent with limit L. So what we have shown is that whenever you have a sequence which is convergent with limit L, no matter which subsequence you take of that sequence, that's also convergent with the same limit L. Okay. So for example, in our previous example where you looked at this sequence whose nth term is given by 1 by n, we know that that sequence is in fact convergent with limit 0, and we saw lots of subsequences of this sequence, a few of those, and it turns out that each of them is then also convergent with limit 0. So for example, this was a subsequence 1 by 2n where n belongs to n, so that's also convergent with limit 0. 1 by n square is a subsequence of this one, that's also convergent with limit 0. 1 by 2 to the power n is a subsequence of this one, so that's also convergent with limit 0. And this subsequence where the nth term is given by 1 by pn, where pn denotes the nth prime, that's also a subsequence of this, and so that's also convergent with limit 0. Now this previous theorem that every subsequence of a given any convergent sequence is itself convergent can sometimes be also used to show divergence. So let's consider this example, namely the alternating sequence where the terms of the sequence are just toggling between -1 and 1. Okay, so -1 to the power n. So this alternating sequence we had seen is not convergent, and we had shown its divergence by using the definition. But now let's see a different proof based on the theorem that we have just learned. And we'll prove this by contradiction. So let's suppose that this sequence, which we call an, suppose that it is convergent with some limit L. Okay, and we'll arrive at a contradiction. Now, this sequence has, of course, subsequences a to n. So we just take out all the evenly indexed terms from this sequence. And also it has as a subsequence the oddly indexed terms, right? So a1, a3, a5 and so on. So both of these are subsequences. Now since we are assuming that this sequence is convergent with limit L, each of these subsequences will also converge with limit L. But you see, this evenly termed subsequence is really the constant sequence 1, 1, 1, 1, 1, and that we know is convergent with limit 1. So this L has got to be equal to 1. Similarly, the oddly indexed subsequence is really the constant sequence -1, -1, -1, -1, and so on, and that we do know is convergent with limit -1. So this L has also got to be -1. So we have got that L should be equal to 1, as well as L should be equal to -1. In other words, 1 should be equal to -1, but that's of course absurd. So we have arrived at a contradiction, and all this happened because we started with the assumption that this sequence is convergent with limit L. So of course that's not true, and so this sequence is not convergent. So the previous theorem can be used to sometimes show divergence as well. Here is one more example, and this is also something that we had considered earlier, namely this sequence whose nth term is given by the sum of the reciprocals of the first n natural numbers. So the nth term is given by 1 plus half plus a third plus so on up till 1 by n. So this sequence we had shown is not bounded, okay, and so it cannot be convergent because every convergent sequence has got to be bounded, right? So since we showed that this is not bounded, we knew that this is not convergent, that is, it diverges. But now let's see a different proof of this, again using the theorem that we have just learned, that every subsequence of a convergent sequence must itself be convergent. So let's suppose that this sequence is convergent with limit L, and let's call this sequence as an, where n belongs to n. So then if I look again at the subsequence with the indices, the even numbers, right? So I look at this subsequence of this one, namely A2, A4, A6 and so on, then that subsequence will also be convergent with the same limit L. So then if I look at the new sequence, which is obtained by term-wise subtraction of these two sequences. So I look at the new sequence whose nth term is given by a2n minus an. Okay, so the first term is a2 minus a1, second term is a4 minus a2, third term is a6 minus a3 and so on. So now that new sequence, which is obtained by subtracting these two term-wise by the algebra of limits, is also convergent. With what limit? The same algebraic combination of this. So since we subtracted the two, the limit of this one is L minus L, which is equal to 0. Right? So this sequence ought to converge with the number 0. That means that if I look at any strip of width epsilon around 0, then far enough in the sequence all the terms are in that strip. Okay. But now we will show that in fact a2n minus an stays bigger than a half always, right? So if I take my strip of width something smaller than half, say 1/4, okay, then we arrive at a contradiction, because all the terms are supposed to lie in that strip, but meanwhile they cannot then be still strictly bigger than half, right? So that's going to be our contradiction. So first of all, let's prove that a2n minus an is in fact strictly bigger than half. So let's see what a2n is. You have 1 plus half all the way up till 1 by 2n. So somewhere down the line you will reach 1 by 2 plus 1 by 3 plus 1 by n, and then you will continue 1 by n plus 1 all the way up till 1 by 2n. Meanwhile, when you are subtracting an, this block will get repeated, you see, because an is just 1 plus 1 by 2 plus all the way up till 1 by n. So these highlighted portions will cancel against each other, leaving only 1 by n plus 1 all the way up till 1 by 2n. Okay, so how many terms are there? How many summands are there? Well, this 2n can be written as n plus n. So this denominator is going from n plus 1 all the way up till n plus n. So what's the change? Well, 1 is increasing all the way up till n. Yeah. So there are n terms over here. And of course, each of them is at least as big as 1 by 2n, right, which is the smallest of these. So the sum of all these is certainly strictly bigger than if the sum which is obtained by replacing each of them by 1 by 2n. Okay, so I replace each of them by 1 by 2n, and hence I get this inequality. And how many such terms are obtained? Well, there were n terms over here, so this is repeated n times. So you have n times 1 by 2n is what this sum is. The n cancels, leaving a half. So a2n minus an for each n is bigger than half. So that always stays above a half. So it cannot reach this strip of width 1 by 4 around 0, for example. Okay, there's nothing sort of special about 1 by 4. Anything less than half would do. Okay, so that would be a contradiction to this fact that this sequence is also supposed to converge to 0, right? So given epsilon equal to 1 by 4, which is positive, since this sequence is convergent with limit 0, there has to exist some index such that beyond that index, the distance of the nth term to the limit, which is 0, is smaller than 1 by 4. And there is our contradiction. Why? Because for all the little n's bigger than capital N, as we just mentioned, this distance is supposed to be less than 1 by 4. But of course, any number is less than or equal to its absolute value, and so this is smaller than or equal to this, and this we had just proved is bigger than a half. So we get the contradiction that half is less than 1 by 4, or in other words 4 is strictly less than 2, which is not true. So our assumption that this sequence is convergent with limit L cannot be true, and so this sequence does diverge. So earlier we had seen a different proof of this, but now we have given yet another proof based on that theorem that we just learned, that if you have any sequence which is convergent, then any of its subsequences is also convergent with the same limit. Okay. Alright, so now we know what a subsequence is, and we are now going to show the Bolzano-Weierstrass theorem. But to do that, we will first prove this theorem. Now, I could have called it a lemma, but in fact, it's a useful theorem in its own right. Okay, useful result in its own right. So let's prove this one first. Okay, so this result says that every sequence has a monotone subsequence. So a sequence has lots of subsequences, okay? But among them, certainly there is one which is going to be monotone. So either increasing or decreasing, okay? Now, the proof of this we'll soon see, but before we see that proof, it maybe helps to first see some idea of what the proof is. So this is sort of an illustrative picture to keep in mind while looking at the proof. Okay, so let's first look at that and convince ourselves that yeah, this result is quite natural, and then we will translate this into a mathematical proof. Okay, so the idea is this. So let's look at the sequence, and I sort of represent the sequence in the following way. Okay, let's assume for the moment that all the terms of the sequence are non-negative. Okay, we won't use that in the proof, but for this idea, it's useful to keep this in mind. Okay, so let's assume that for the moment that all the terms of the sequence are non-negative, and imagine that you have all the terms represented like this. So here are the indices, and you think of sort of buildings with height equal to the term of the sequence. Okay, so this first building has height a1 if the sequence is a1, a2, a3 and so on. The second building has height a2, the third building has height a3 and so on. And think of these buildings as sort of hotels, and far away at infinity there is the sea. Okay, and a hotel is said to be a sea view hotel if from the top floor you can view the sea. So there is not going to be any other hotel which obstructs the view. So the heights of all the subsequent terms of the sequence are smaller. Okay, right. So with this picture in mind, there are only two possibilities. Okay, either there are infinitely many sea view hotels, or there are finitely many sea view hotels. If there are infinitely many sea view hotels, we'll see that you get a decreasing subsequence, and if there are only finitely many sea view hotels, we'll see that we arrive at an increasing subsequence. Okay, so for example, this first hotel is not a sea view hotel, because if you go on the top floor, well, there is this second hotel which is blocking the view. The second hotel also does not have the sea view property, because from the top floor you cannot view the sea, because there is this third hotel which is obstructing the view. Now suppose the third hotel has this height and all the subsequent hotels have smaller height. Then from the top floor you can view the sea. You see, there is nothing obstructing it because all the subsequent hotels have smaller height. Similarly, the fourth hotel is not a sea view hotel because this fifth hotel is blocking the view. The fifth hotel seems to be a sea view hotel because from the top floor you can view the sea, provided that all the subsequent hotels have smaller height. Okay. Similarly, the sixth hotel is not a sea view hotel. Oh, the ninth hotel blocks the view. Seventh hotel is not a sea view hotel because again the ninth hotel blocks the view. Eighth hotel is also not a sea view hotel because the ninth hotel blocks the view. The ninth one seems to be a sea view hotel provided that all the rest have smaller heights. Similarly, the 10th hotel seems to be a sea view hotel provided all the rest have smaller heights. 11th hotel is not a sea view hotel, and the 12th hotel is a sea view hotel. Okay, so as I mentioned, there can be only two possibilities. Either there are, for your given sequence, the number of sea view hotels is infinite. Okay, let's show that in that case, if you just take the subsequence comprising these sea view hotels, okay, then you will, since this list is infinite, you get infinitely many terms and they are decreasing. Of course they are decreasing. Why? Because you see, suppose that this is the index an1. So an1 is a sea view hotel, so everything beyond is going to be smaller. In particular, an2, the second hotel with the sea view property, is going to be smaller. Okay, and then I'm taking the next sea view hotel. Well, everything is smaller than this, so in particular an3 is going to be smaller than an2. Similarly, the next sea view hotel is going to be smaller than an3, an4 is less than smaller less than or equal to AN3, and so on. Okay, so these infinitely many sea view hotels then is your subsequence, which is decreasing. Okay. Now, how about the other case when the number of sea view hotels is finite? In this case, I will produce a subsequence which is increasing. How do we do that? Well, suppose you first walk along this array so that all the hotels with the sea view property are behind you. Okay, so no more sea view hotels are left now. And then you take the first hotel as the first term of your subsequence. Well, that's not a sea view hotel because all of them you have passed. So there must be a hotel which prevents its view. So you take that as the next term of the sequence. Well, that's going to have a bigger height because that was blocking the view. And again, that's not a sea view hotel because everything with the sea view property has been passed. So there must be yet another hotel which blocks the view. You take that as the next term of the sequence. So that's going to be bigger than where you were at. Okay, and then again, that's not the sea view hotel. So there must be yet another hotel. You take that as the next term of the subsequence. So that's even bigger. And then again, that's not a sea view hotel. So there must be still something bigger. And that's not a sea view hotel, so there must be still something bigger, and so on. So now you get an increasing subsequence, and since none of them have the sea view property, there will always be something which blocks the view. So in this way, you get infinitely many terms, okay, and you get an increasing subsequence. Okay, so sort of pictorially, this proof is fairly clear that okay, you can either have one case or the other. In one case, you get decreasing; in the other case, you get increasing, and so you are guaranteed a monotone subsequence. Okay, so now we will write this down using only mathematics, but the same kind of ideas will be there, but of course to write everything down we'll be sort of extra careful. Okay, so here is the proof. Okay, so let's denote our sequence by an. Okay, and just as before, what did we do? We consider the set of all the hotels with the sea view property. Okay, by the way, now we are not assuming that an is non-negative. They can be negative, positive, or zero, doesn't matter. So you define this set, which you should think of as collecting all the indices of the sea view hotels. So these are all the m's in n, such that, well, this is a sea view hotel, so for anything beyond, the height should be smaller. So for all the little n's which are beyond this m, an is strictly less than am. Okay, so the height is smaller, and so this is exactly those indices of the sea view hotels. Okay, now either this set can be infinite or it can be finite. Now if it is infinite, we'll produce a decreasing sequence just as before, and if S is finite, we'll produce an increasing sequence just as before. Okay, so suppose S is infinite. Well, then you can list these natural numbers, there are infinitely many of them, in increasing order. So you list them as n1 strictly less than n2 strictly less than n3, and you get an infinite list. And you simply take the terms from the original sequence corresponding to this list, and we are automatically guaranteed a strictly decreasing sequence. Why? Because you see that n2 is strictly bigger than n1 and both of them are in the set. If I look at n1 in this set, then n2 is bigger than 8, so an2 will be smaller than an1, right? Exactly as over here. Now n2 is in here, and so for anything bigger, in particular n3, the height of an3 will be smaller than an2, right? So because of this, because of the way this set is defined, and when you have these terms in the set, you automatically get this chain of inequalities. So exactly as before, we get a decreasing sequence. What happens if S is finite? Well, in that case, we will construct an increasing sequence. How had we constructed it like earlier? You first pass all the sea view hotels, and then you take the first hotel. Well, that ain't a sea view hotel, so there must be something which prevents the view. You take that as the next one. You move to that one, and well, that's not a sea view hotel, so there must be something which blocks the view. So you take the next one, and you're guaranteed that this will continue forever because all the sea view hotels had passed. Okay, so that's exactly what we are going to do. We are going to construct this increasing sequence recursively. Okay, once I am at a hotel, I'll tell you how to choose the next one. Well, it will be the next one which blocks the view. Yeah, so let's define this increasing sequence an1, an2, an3, so on recursively. So I'll tell you once you are at a certain stage how to choose the next one. At the first stage, you have passed all the hotels with the CV property behind you. Okay, so S was that set of indices which had the CV property. So you take the maximum of those and you add 1 to it. So now you are at the first building beyond the last building with the CV property. But of course, S might be empty, in which case you just take N1 as 1 if S is empty, and if S is not empty, you take the maximum of S. Remember that S is finite, so this maximum exists. A finite list of natural numbers always has a maximum, and you add 1 to it. Okay, so now you are at the first building after the one with the CV property. Okay, so N1 there is no problem constructing. And now, since we are going to give a recursive argument, let's suppose that we have already constructed N1 up till Nk. So this K might be actually 1 at the first step. Okay, and they have been constructed such that you have already got an increasing list of numbers so far. So an1 is less than or equal to an2 and so on up till ank. Okay, so what I'm going to tell you is that in the previous case, I'm having constructed this sequence partially. I'm going to tell you how to construct the next one. Okay, so how did we construct that? Well, you took the first hotel which blocks the view. So having constructed n1 to nk, you take nk plus 1 as that index which is beyond this nk1 where you are at, such that the height is bigger, right? So it's the first one, hence you're taking the minimum. So I'm taking that index which is beyond where I'm at, such that the height is bigger, and you're taking the first such one. So that's why the minimum is there. Okay, so this is basically the index of the first hotel which is blocking the current hotel that you are at. So let's look at this set. Let's call it S prime. Okay. Now for this minimum to exist, this S prime, which is a subset of natural numbers, I'm only putting in natural numbers in there, should be non-empty, right? So I should first show that S prime is non-empty. So let's first prove that. Okay. So suppose that S prime is empty. What does that mean? That means that there is no M in this set. Right? So no matter which M I take, if it satisfies that M is bigger than Nk, this cannot happen. So Am is less than Ank. But that means that whenever I'm taking any index which is bigger than this Nk, the height is smaller. And so Ank is a CV hotel. What does that mean? That means that this Nk belongs to this set S. But that cannot happen, you see, because nk is bigger than or equal to n1, and n1 was maximum of s plus 1, right? So in particular, this nk will be, of course, is bigger than or equal to n1, which is maximum of s plus 1 in the case when s is non-empty, and this is strictly bigger than maximum of s, but that cannot happen because maximum of s was supposed to be bigger than or equal to nk, because nk belongs to s and this is an upper bound of s, right? So maximum of s was supposed to be bigger than or equal to nk, but now I've got that actually it is strictly less than nk. Yeah, so that cannot happen. So this was the case when s is non-empty, but if s is empty also, this is not possible, because we are saying that nk belongs to s, but s was supposed to be empty, so there cannot be anything in s. So in either of this case, we have got a contradiction. So because of this contradiction, this S prime cannot be empty. It's a non-empty subset of the natural number, so it has a minimum, and that I take as my nk. Now this nk being the minimum of this set, it belongs to the set. So this nk plus 1 has both of these highlighted properties. So first of all, this nk plus 1 is bigger than nk, and moreover ank plus 1 is bigger than or equal to nk. So I have managed to do this inductive step. So knowing what n1 to nk are, which have this property, I tell you how to go to the next one, nk plus 1. Okay, and in this way I have constructed this increasing sequence recursively. So in the case when s is finite, we get this increasing subsequence, whereas when s was infinite, we had seen that you get a decreasing subsequence. So these are the only two possible cases, and in each case we have produced a monotone subsequence. So this proves this theorem that every sequence has a monotone subsequence, and this will be used now to show the Bolzano-Weierstrass theorem. So let's first see what is the statement of the Bolzano-Weierstrass theorem. It says that every bounded sequence has a convergent subsequence. So the given sequence is bounded. It may not be convergent, but we are assured that it has at least one convergent subsequence. Of course, it can have more than one. For example, if I look at this divergent sequence, it is not convergent. It is bounded, and so we are guaranteed that it has a convergent subsequence. In fact, we know that, for example, the evenly indexed subsequence is 1, 1, 1, which is convergent with limit 1, but for example, the oddly indexed subsequence is minus 1, minus 1, minus 1, and that's also convergent with limit minus 1 this time. Okay, so there can exist more than one, but what this Bolzano-Weierstrass theorem is saying, that there is at least one subsequence which is convergent. So the proof is very easy now that we have the earlier result to use, which we have proved. So suppose that our given sequence is an, which we have been told is a bounded sequence. So that means that there exists a bound, a positive number, such that for every index n belonging to the set of natural numbers, you have that the modulus of the nth term is less than or equal to m. Now this is a bounded sequence, but of course it's a sequence, so we are guaranteed by the previous theorem that there is a monotone subsequence of this sequence. Every sequence has a monotone subsequence. So let's take one such monotone subsequence. Okay, maybe it is let's denote it by a and k. Okay, so this is a monotone subsequence of this given sequence. Now this subsequence is also bounded, because boundedness is inherited by any subsequence. Why is that so? Because for this to be bounded, in fact the same bound works, you see, because this is true for every index, in particular for any nk, that is some natural number, the mod of that is going to be less than or equal to m, because for every index this is true. So this subsequence is in fact a bounded sequence, and also we had chosen it so that it was monotone. So it's monotone and bounded, so it's convergent. Done. Right? Because of the theorem that we had learned a while ago, we had learned that monotone and bounded sequences are convergent. So this subsequence, which is both monotone and bounded, is convergent. So this proves the Bolzano-Weierstrass theorem. This is an important result, and let's see, for example, one application of this. So a while ago we had met this interval. So a and b are real numbers, a is strictly less than b, and then this interval is the set of all x's which are bigger than or equal to a and less than or equal to b. Okay, and we had called such a interval a compact interval. Okay, now this compactness is a certain property which you learn in MA 203, and in the context of this interval, what it really means is that whenever I take a sequence in here, then it has a convergent subsequence whose limit is again in that set. Okay, so that's what I want to show, and I will show this using the Bolzano-Weierstrass theorem. So what I want to show is that every sequence in this interval has a convergent subsequence whose limit is again belonging to this interval. Okay, so let's prove that. So that's my claim which I want to prove, and we will prove this using the Bolzano-Weierstrass theorem. So suppose I take any sequence in here. So what does that mean? Let's call the sequence xn. Okay, to say that this sequence is in this interval means that xn belongs to it. So xn is bigger than or equal to a and less than or equal to b for every index n. So this means that if I look at the set of all xn's, then that has an upper bound b and has a lower bound a. So that set of values, you put all the terms in a set, that set is bounded. And we had seen a while ago that that means that this sequence is a bounded sequence. Now since this is a bounded sequence, by the Bolzano-Weierstrass theorem, it has some convergent subsequence. Let's call it xnk. Okay, and let's call its limit as L. Now I want to show that this L again belongs to this interval. So I want to show that L is bigger than or equal to A and less than or equal to B. How do we do that? Well, I know that for every k, xnk, so since xn itself satisfies this, also xnk's being a subsequence also satisfies this. Okay, this is true for all n, in particular for the nk's. So for every k, this subsequence terms are in between a and b, so they are bigger than or equal to a and less than or equal to b. Forget about this inequality for the moment, let's focus on this. So for all the k's, xn1 is bigger than or equal to a, xn2 is bigger than or equal to a, xn3 is bigger than or equal to a, and so on. So you look at two sequences, the constant sequence a, and the sequence whose kth term is given by x and k. Then we have that for every k, the kth term of this sequence is bigger than or equal to the kth term of the constant sequence a. Okay, but then a while ago you had learnt this exercise which said that whenever term wise one sequence dominates the other, bn is bigger than or equal to an for all n, then the limits also inherit this inequality. So the limit as n tends to infinity of bn will be then bigger than or equal to the limit as n tends to infinity of an. Okay, so this was this exercise 2.18. The application of this we can summarize by passing to the limit as k tends to infinity. That just means that whenever term wise you have inequalities, okay, so then the limit also obeys that. That is succinctly referred to as passing to the limit as k tends to infinity. So the limit as k tends to infinity of this one is L, and the limit as k tends to infinity of this constant sequence a is a, and so by this exercise 2.18 we have that L is bigger than or equal to a. Similarly, now let's focus on these inequalities. So for each k, the kth term of this subsequence x and k is less than or equal to the kth term of the constant sequence b, right? And so the limits also obey the same inequality. So the limit of this, which is L, is less than or equal to the limit as k tends to infinity of this constant sequence b, which is b. So you get also this inequality. So L is in between a and b, right? So L belongs to this interval. So what we have shown is that when I took this sequence, it has this convergent subsequence guaranteed by the Bolzano-Weierstrass theorem, and whatever its limit is, we in fact showed that it again belongs to this set. So every sequence in this interval has a convergent subsequence whose limit is again in that same interval. Okay, and somehow this property is compactness in this context, and that you will learn in MA 203. But for us, the only point of this example was that we proved this statement, right? That this interval has this property that no matter which sequence you take, it has some convergent subsequence whose limit is again in that same set. Okay, and we did this by using the Bolzano-Weierstrass theorem. So sort of to look at a concrete example to see this in action, let's consider a equal to -1, b equal to 1. Okay, so I'm looking at this compact interval, and as my sequence I take cos n. So I'm thinking of n radians where n ranges over all the natural numbers. Okay, so cos 1, cos 2, cos 3 and so on. So that's a sequence in here. By what we have learned, there must exist a subsequence of this sequence which is convergent with limit again belonging to this interval. Okay, so there exists some list of infinite list of natural numbers n1, n2, n3, so that if I look at the subsequence obtained from these indices, so cos nk, that is convergent with limit again belonging to over here. But if you look at what this sequence is, it is actually quite erratic. Okay, so here is 1 radian, it's about 60 degrees, and then the cos of this one is really the projection of this point on the unit circle onto the real line. Okay, so this distance is cos 1 if this angle is 1 radian. Then what's cos 2 radian? Well, you double this angle, you will be on this point in the unit circle, its projection on the real axis, that's what cos 2 is. So it should be negative, and indeed if you use your calculator you will find this value. Then cos 3, you triple this angle, that will be somewhere over here, and that will be negative and somewhere close to -1, and indeed it's something like this. Cos 4 similarly, is negative, and somewhere over here it's actually minus 0.65 blah blah blah. Cos 5 is positive now and it's 0.28. Cos 6 is this one, and as you keep rolling around in the circle you will get all these erratic values. Okay, so cos n discernibly has no sort of pattern in there except that the values are jumping all over the place, but nevertheless it has a subsequence which converges to some number in between minus 1 and 1. In fact, much more is true. No matter which L you take, okay, I just close my eyes and take a value over here. In fact, there is a subsequence of this sequence cos n which has limit exactly that. This happens with every L in between minus 1 and 1. That can be shown. That proof is beyond the scope of this course, but it's an interesting fact. So somehow, suppose that I had closed my eyes and taken this number, okay? Then if I take any small tiny epsilon width over here, then I'm guaranteed that, well, there is a subsequence of this original sequence which converges to this. So it will lie in that little tiny epsilon width. That means that this sequence itself will have to keep visiting that little neighborhood infinitely many times, and this happens with every L. Okay, so it is quite an interesting property that somehow this sequence of values is sort of uniformly distributed. It keeps jumping, but it sort of does that in a way that it keeps visiting every region in this minus 1 to 1. Okay. Anyway, we cannot prove this interesting fact right now, but for those who are interested, I have given a reference to this. For example, this Niven's book on irrational numbers contains a proof of this. Okay, so this was just a curious fact, and let's continue with one last consequence of this Bolzano-Weierstrass theorem, which I call the nested interval property, okay, of the real numbers. So what does this say? Suppose I have a list of sets of this form. So for every natural number, I have a set which I call Im, which comprises real numbers which are bigger than or equal to am and less than or equal to bm. Okay, and this list of sets I1, I2, I3 and so on are nested in the sense that I2 is included in I1, I3 is included in I2, I4 is a subset of I3, I5 is a subset of I4 and so on. Okay, so if I draw I1 in blue and it looks like this compact interval from A1 to B1, and I2 then is something which is contained in I1. So maybe it is like this red compact interval A2 to B2. Then I3 is included in is a subset of I2. So maybe it's the green set A3 B3 and so on. So I have such a nested list of sets. Then it turns out that if I take the intersection of all of these sets, then the intersection is not empty. Now these sets were of a particular type. You have less than or equal to on both sides. Long ago there was a homework problem which was assigned where the intervals in question were open and then the intersection was empty. Okay, so the intersection can be empty. It's not just because of the nestedness, but it's because of this fact that somehow these intervals are compact, right? So you have less than or equal to, and that somehow saves the day. Okay, so let's prove this, and this fact is called the nested interval property. What we want to show is that this intersection is not empty. The way we are going to do this is I'm going to first produce a bounded sequence. By the Bolzano-Weierstrass theorem, it will have a convergent subsequence. If the limit of this convergent subsequence is A, right, then we are going to show that in fact A will belong to this intersection, and so this intersection cannot be empty. Okay, so that's the sort of outline of the proof, but let's see how the sequence is constructed. So I just take these left endpoints as my sequence. So AN is the left endpoint of this IN, and since IN is contained in I1, this AN belongs to I1. So this AN is an X which satisfies this thing with m equal to 1. So AN is bigger than or equal to A1 and less than or equal to B1. So this left end points, they are all in this big blue set, right? And so they have an upper bound and a lower bound. Okay, so this sequence an is bounded. By Bolzano-Weierstrass theorem, it has a convergent subsequence, right? So there is some subsequence, let's call it a and k, and it converges to some number a. Now I'm going to show that this a in fact belongs to each of these IMs, so it belongs to that intersection. Okay. So what do I have to show? To show that a belongs to each IM, I have to show that a is bigger than or equal to am and less than or equal to bm. I break it up into two parts. First I'll show that for each m, a is bigger than or equal to am, and then later I'll show that also for each m, a is less than or equal to bm, so that a belongs to each IM and hence it belongs to the intersection, and so the intersection cannot be empty. So that's where I'm heading. So I have to prove these two claims, that for each m, a is bigger than or equal to am, and later we'll also show that it's less than or equal to bm. So to show that for each m, a is bigger than or equal to am, let's suppose that this is not true. So there must be some m which where things go wrong. So there is some m such that this is not happening. In other words, am is actually strictly bigger than a. In other words, this epsilon, which is am minus a, is a positive number. Okay, so somewhere down the line there is am. Let's suppose that this is where am is. Okay, and am minus a is positive. That means that a is somewhere over here. Okay, but you see that that a and k is going to be eventually some interval which is inside am, right? So a and k is going to go on the right of this am, but it's also supposed to approach this a, because a was the limit of this a and k. So that cannot happen. So that's going to be the source of our contradiction. Okay, so let's give the details now. So for this positive epsilon, since this subsequence converges to a, there is some index, let's call it capital K, such that for every little k bigger than capital K, the kth term of the subsequence a and k, its distance to a is less than the epsilon, which is am minus a. Okay, so a and k minus a is of course less than or equal to its own mod, which I know is less than am minus a, so the a's cancel and I get a and k is less than am for every little k which is bigger than k. Okay, but now I'm going to show that a and k is actually to the eventually goes to the right of am, right, because of this nested property. So if I take any k which is strictly bigger than m, then we know that nk is bigger than or equal to k because of that inequality, observation inequality that we had proved long time ago. Whenever you have a list of increasing natural numbers, the kth member is bigger, at least as big as k. So when I take a little k which is bigger than m, nk which is bigger than or equal to k is bigger than m. So this nk is bigger than m. But then this nkth interval, this nkth set is going to be inside im, yeah, because of this nestedness. And whenever you go beyond, then that interval is in there. So ink is contained in im. Okay, what does that mean? That means that a and k, which is inside I and k, that is going to be in im. In particular, it's bigger than or equal to am, right? So of course both of the, so this happens for all the k's beyond this capital K, and this happens for all the k's beyond m. So if I take a little k which is both beyond m and beyond capital K, then both of these highlighted things should hold. But of course that's impossible by the trichotomy law, right? So it cannot be the case that a and k is less than am and also bigger than or equal to am. Okay, so this contradiction shows that our original assumption was not true. So it cannot be this case, and so this has to hold for all the m's. Okay, so I already know that this a is bigger than or equal to am for all m. Alright, so now let's also show this claim B, which says that for each m, a is less than or equal to bm. So let's take any m, and then we know that after a certain point, this nk is going to surpass m. So ink is going to be in im. So all of these a and k's beyond a certain point are going to be less than or equal to bm, and then we pass the limit as k tends to infinity, so that then you get a is less than or equal to bm. So that's the plan, and now let's give the details. So let's fix an m, and we know from our inequality that we had observed long ago that for each k, nk is bigger than or equal to k. So if I take any k bigger than or equal to m, I have that nk, which is bigger than or equal to k, is also bigger than or equal to m. So for all the k's beyond m, you have nk is bigger than or equal to m, and so by the nested property hypothesis, you have that ink is contained in im, right? But a and k of course belongs to I and k. So a and k also belongs to im. In particular, a and k is less than or equal to bm, and this happens for all the k's which are bigger than m. So think of the two sequences which are indexed by k, and you have that for all the k's beyond m, a and k is less than or equal to the kth term of this other sequence, which is the constant sequence bm, bm, bm. So m was chosen at the outset, something fixed, and then we have that for all the k's bigger than or equal to m, a and k is less than or equal to bm. So by passing to the limit as k tends to infinity, the limits also respect the inequality, and so the limit of this thing, which we know is a, is less than or equal to the limit of the constant sequence bm, 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 which is of course bm. So I've got a is less than or equal to bm, and since the choice of m was arbitrary, it follows that this is true for all the m's. So we have got also this claim B. So putting the two claims together, we have that for each m in n, a is less than or equal to bm and bigger than or equal to am. In other words, a belongs to this im. Okay, for all the m, a belongs to I1, a belongs to I2, a belongs to I3, and so on, and so it belongs to their intersection. And so the intersection is not empty, because here is an element in there, namely a. Okay, so what we have managed to show is that if I look at these left end points, then that sequence was bounded, that had a convergent subsequence by Bolzano-Weierstrass theorem, and whatever its limit is, in fact it belongs to this intersection. Okay, so this property of the real numbers is called the nested interval property. Alright, so that finishes this lecture, and what's now left is chapter 3. So the last 2 weeks of this Michaelmas term will be on chapter 3, which is going to be on continuous functions. Okay, so next time we will discuss what is this concept of continuity, and then we'll look at some properties which are possessed by continuous functions. Okay, so we'll stop here.